Hi folks, they give us the first three patterns here. This is question 10. It's integer coordinates. We have to plot the next one now. It's just seeing what's across, so that one is obviously one away from the y-axis, so you just have to do that each time. Everything is symmetrical here. And so you just have to be careful, so there's nothing there, for example, so therefore there should be nothing there. So it's that kind of a thing. So just be careful and plot them. And yeah, that should be it. Right, so in pattern 2000, there are 4 points that are a distance of 2000 units from 0, 0. So if you think about it, in pattern 1, uh, that point is 1 away, the top point is 1 away, that point is 1 away, that point is 1 away. That's in pattern 1. Then in pattern 2, that point there is 2 away, that point there is 2 away, that point there is 2 away, that point there is 2 away. So you can see what's happening. So in pattern 2000, if we just go to if we start at the origin and go 2000 to the across the x-axis, that will give me the point 2000, 0. If I was to go to the left 2000, it would give me minus 2000, 0. If I was to go up 2000, it gives me 0, 2000. If I was to go down 2000, it's 0, minus 2000. That's it. What's the smallest value of n for which 4, 4 is in pattern n? Well, if we think about the point 4, 4, it says not to draw on your part A, not to draw on the diagram from part A, because obviously you lose marks if you put in more dots when part A is being marked. So I can draw on pattern 2 though. So the point 4, 4 is here. So we want to see how many patterns it goes out by. So for pattern 2, it's the point 1, 1 is in pattern 2. So then for pattern 4, I assume the point 2, 2 is in pattern 4, is it? Yeah. Okay, it's that one there. I shouldn't be drawing on the diagram. But it's just to show you. So, see the pattern 3, none of those points are on it, 1, 1 or 2, 2 or any of them, because it skips one each time. For example, there and there and there. That's the ones we want. Okay, so pattern at the odd number patterns won't work. So for pattern 6, 6 has the point 3, 3. So there pattern 8 has the point 4, 4. So it's pattern 8. Okay. So simple if you can understand that. So pattern 8. Alright. Rearrange the formula. T is equal to 2n plus 1 to write n in terms of p. So that's quite simple. We just move the 1 over to the other side. So we get t minus 1 is equal to 2n. N is equal to t minus 1 over 2. Then we're going to put t minus 1 over 2 in everywhere in here. So q of n is equal to t minus 1 over 2 plus 1 all to be squared over 2 times t minus 1 over 2 plus 1 all to be squared. That equals t minus 1 over 2 plus 1 squared over, if I multiply the 2, the 2's cancel out, so it's t minus 1 plus 1, so that's just t on the bottom. And it's still to be squared. On top, if I change the 1 in there, the one that's by itself on the top, to 2 over 2, that gives me, it just gives me a common denominator, so I get t minus 1 yeah, I get t minus 1 plus 2 t plus 1 over 2 all to be squared over t squared. Now, if I square everything on the top, I just get t plus 1 to be squared over 4, because 2 squared is 4, all over t squared. And then I'm going to take the t squared that's on the bottom, so that t squared, and I'm going to divide by it. So when you divide fractions, you flip the second one upside down and multiply. So that gives me, run out of space now. So it's t plus 1 squared over 4 multiplied by 1 over t squared. And that gives us then what we should get. So it's t plus 1 squared over 4t squared. That's it. And next part is getting the limit. The highest power of t is t squared, therefore we're going to divide everything by t squared. We have t, so limit as t tends to infinity is t squared over t squared. Oh yeah, I didn't do that in the last part actually, and you need to multiply out the top as well, just multiply out the square. I didn't do that, but you should be able to multiply it out anyway, so you get t squared plus 2t plus 1. So in this one, t squared over t squared plus 2t over t squared plus 1 over t squared over 4t squared over t squared equals, top we just get 1 plus 0 plus 0. The bottom we just get t squareds cancel out and we get 4. So 1 over 4. And hn is the total number of dots in pattern n. Therefore h1, so you just have to see how many total dots in pattern 1, and there's 4 dots. You can count them up. When n is a natural number, h of n plus 1 can always be found. H of n plus 1 is equal to hn plus 2n plus 3. Using this fact, prove the identity on the grid. Use proof by induction. Right, so long enough. The last part. To prove by induction, we're going to prove or show true for n is equal to 1. So therefore hn is equal to 1 plus 1 squared. 1 plus 1 is 2, 2 squared is 4. So 4 is right because it gives us the answer that we had for the first bit. So now we're going to assume true for n equals k. So h of n is equal to k plus 1 squared. We're going to assume that that's true, and then we're going to show true for n equals k plus 1. That would be, well, h of n would be equal to k plus 1 plus 1 squared. So that's k plus 2. And really, this is h of n plus 1 now that we're finding. So we have to show that that's true then. Now we already know, they told us in the last bit what h of k plus 1 is. So h of k plus 1 is hk, which is the thing we assumed. So that's k plus 1 squared, and then plus 2k plus 3 is equal to k plus 2, k plus 2. So it's just showing that both sides are the same, I think. So k squared plus 2k plus 1 when you multiply out the brackets there, plus 2k plus 3. So that gives me k squared plus 4k plus 4 equals. So here we get k squared plus 2k plus 2k plus 4. K squared plus 4k plus 4. So that's it. That's that proven. So that's it. That's all for that paper.